Hey everybody, welcome to 5.1, Integer Addition and Subtraction. This section really marks being very close to the end of the semester for us. So just hang on, we're almost there. I think you'll like the next couple of sections. So this integer addition and subtraction is something really moving into middle school for kids. So the idea that positive and negative numbers describe opposites or things with opposite directions or value. Think temperatures, elevations, money. Money's the real key here. They can represent the use of positive and negatives in the real world. And when we talk about positives and negatives, we're talking about rational numbers on a number line. They need to understand where, we talked earlier in the semester about how having kids be solid with a number line as younger kids really helps them at this point, because they'll be able to put negative numbers on a number line to the left and understand that they're smaller. Additionally, they have to understand the idea of opposite of numbers, that when they get negative numbers, this also opens up the coordinate grid to them. So it lets them have 4 quadrant values, because there's negatives and negatives over here, right, on this side. And then it's really about position and where things are. Having negative numbers in their repertoire opens up a whole new world of stuff for kids, but it also really fries their brains to a degree, especially when it's new. So at this point, when we're talking about integers, we're really talking about the whole group of numbers here, okay? Up to this point, we've been talking about natural numbers and zero, which is whole numbers together. Now we're jumping in to add the negatives, which gives us the whole family of integers. Notice that at this point, we are not talking about fractions or terminating or repeating decimals. If you have to take 105, that will happen in the next course. So when we talk about integers, this is what we're talking about. The set of integers is denoted by a big I, just like whole numbers was a W. Natural numbers was an N, okay? So the set of integers is negatives all the way down here from negative infinity, all the way up here to positive infinity. Negative numbers are the opposite of positive numbers. -4, for example, is the opposite of 4. +3, for example, is the opposite of -3. Pretty straightforward. This is stuff you know, but for younger kids, this is like, wait, what? It sort of blows their minds. So find the opposite of each number. What's the opposite of 6? Well, -6, right? The opposite of 7 is -7. The opposite of -52 is plain old +52. The opposite of 10,000, -10,032 is +10,032, and so on. You, I'm sure, don't need 7 examples to make this work, but you do have to help kids understand that it occurs, this is the case, no matter how big or small a number is. If I had 1,000,000, the opposite is -1,000,000, okay? So there are lots of ways to model integer addition and subtraction. It's really important that you make it tactile for kids, because as I said, this really does fry some of their brains. The most common model for kids to use initially is with chips. Think bingo chips. So what happens is one color, in this case red, represents a negative number. So for us, red, and I always make a little key somewhere, red is going to be negative. In this case, black is positive, okay? The key to this is that each pair of positive and negative chips together make a 0. I'm going to say it again, just to make sure, because this is the key to this idea of a 0 pair. A positive chip, a black, which is a a positive one, plus a red, which is a -1, together make a 0. So that is the key to this, because what's going to happen when I have a problem like -4 plus 3 is that I'm going to make zeros. I can match these guys up to make a 0, 0, 0. What's left is a -1. So -4 plus 3 is a -1. So draw some chips and use them to find the answers to these questions. -3 plus 9, -4 plus 2, 3 minus 8. think about how you would represent this. It's not about knowing the answer. I'm sure you know the answer. It is about how to draw it as a picture, okay? So take a minute and do that. All right, for this first one, I'm going to draw -3 and +9. I try to line mine up. And then we're going to make zeros. So I have 1, 0, 2, 0, 3, 0. What's left? +6. For -4 plus 2, I got 1, 2, 3, 4 red circles, 1, 2 black ones, and then we're going to zero out what we have matching. So I can zero out at 1 set, 2 sets. What's left? -2. All right, this is a strange one, but what you teach kids eventually, right, is to rewrite this as an addition problem. 3 minus 8 is really the same thing as 3 plus a -8. So I can recontextualize a subtraction as adding a negative. And this is the part that really fries kids. They're like, wait, subtracting didn't, why? I don't understand. You have to do this a bunch and prove to them how this works, okay? So we're going to make 3 black circles, 3 positives, 1, 2, 3. And I'm going to make 8 negatives, 1, 2, 3, 4, 5, 6, 7, 8. And then I'm going to zero out my zeros. 1, 2, 3. What's left? -5. Okay? If you need to do more of these, you should just play around with it. If you have bingo chips at home, maybe you do. I do. But I could be the weird one here. Play around or make little shapes out of paper or something. But this is probably the most important model next to the number line here. The second model is the charge field. So what happens is you give kids chips and you let them play. And then you have them write down their problems and their answers. That's fine. The charge field is sort of like one step more abstract for kids. So it's the same idea, except instead of moving around chips with my fingers, I'm going to draw pluses and minuses. Okay? Same sets of 0 pairs work. Same idea happens. It's just that we're not going to move stuff around anymore. We're just going to draw pictures, okay? So this is 3, +3, plus a -5. So I'm going to make my zeros. What's left is -2. So do the same thing, make charge fields for the problems here, okay? Take a minute and do that. So you're drawing plus signs for positive numbers and minus signs for negative ones. That's all. All right, so the first one is -9 plus 6. My pluses are going to be really sloppy because I'm drawing on my computer. I'm sorry. 5, 6. This works the same way we make zeros. 1, 2, 3, 4, 5, 6 zeros leaves me with -3. Remember a problem like 16 minus 8. We're going to recontextualize this addition. 16 plus a -8. Okay? So I would draw 16 pluses. Oh, I'm going to be here a while. I'm almost there. 6, 7, 8. And then 8 minus signs. 1, 2, 3, 4, 5, 6, 7, 8. I'm going to make my zeros. I can make 8 zeros. And then I'm left with a +8. Okay, you see where this is going. So you should be able to draw the models for 6 plus a -11 and get a -5 in your picture, and -10 plus 1 and get a +1 in your picture. Okay. The third model is one step even further abstract, is to take all of this and put it on a number line. Okay? Remember, on a number line, positive integers are represented by moving forward. We think about moving forward as moving in the positive direction, right? We move to the right. Negative integers are moving backwards to the left. So if I have -3 plus a -5, I'm going to start at 0 and move -3 to the left, negative number. Think of this plus as an and. So I have -3 and -5. So from -3, I'm going to move -5 more and -5 to end up at -8. So do these on a number line. I'm going to draw one big old number line, and then I'll use different colors. So here's my number line. You try them while I'm drawing. Okay, 0. A couple more digits here. All right, so 4 minus 7, we're going to think of as 4 plus -7. So we're going to do that one in red. So I'm going to start by moving to 4. 1, 2, 3, 4. That's 4. And then I'm going to move -7, which means I'm going to move from there to the left. 1, 2, 3, 4, 5, 6, 7. Gets me to -3. So 4 plus a -7 is -3. Let's do -6 plus 4 in green. So I'm going to start at 0, and I'm going to start to the left at -6. 1, 2, 3, 4, 5, 6. There's my -6. Then I'm going to move to the right because it's plus 4. 1, 2, 3, 4. That gets me to a positive 2, or sorry, a -2. And I just drew a 3. All right. -3 and -7, opposite direction. So first, I'm going to go -7 to the left because it's a negative number. So there's my -7 and -3 more. So there I am, all the way at -10. 7 minus 11, remember, we're going to reorganize. 7 plus -11. So I'm going to do that in pink. I'm going to go over this way to 7, 6, 7. And then I'm going to go backwards 11. 1, 7, 8, 9, 10, 11. So that gets me to -4. Okay, see how these work? Okay, there is another model in here, which is a pattern model. What happens is some kids really need to think about this different. This is not for every kid, and not everybody will even go like, oh my gosh. But what happens is you can start, kids can back into negative numbers. You can start with the numbers you know and sort of work your way back to negative. So I know 4 plus 3 is 7. I know 4 plus 2 is 6. I know 4 plus 1 is 5. I know 4 plus nothing is 4. That means if I'm watching 7, 6, 5, 4, 4 plus -1 is 3. 4 plus -2 is 2. 4 plus -3 is 1. And we work our way down by using the pattern, okay? So if I wanted to do 6 plus something, I would start with something I knew. Remember, we're going to write this one as 6 plus a -7. But maybe I can start with 6 plus regular 2, positive 2 is 8. And then, sorry, I'm going to change my color. 6 plus 1 is 7. 6 plus 0 is 6. 6 plus a -1 is 5. 6 plus a -2 is 4. And then I can keep going all the way down and continue my pattern until I can answer all the questions I have. It's a fine way to do it if kids need to think that way to start. This is sort of a strategy that you'll see kids use very early on. It's not one that should stay around forever, hopefully, but the more you do, the more, the less this should be necessary, but it does really help some kids to sort of see where it all comes from. All right, part and parcel of this section is the idea of absolute value. When we write a number in the absolute value sign, like this, it's defined as the distance on the number line from 0 to that number. It is always positive because it's a distance, right? We don't measure distances in negatives. I don't say to you, oh, I live -3 miles from here. You would think I was crazy. So the absolute value of 4 is 4, so it's 4 units from 0. The absolute value of -4 is also 4 because it is 4 units from 0, okay? If the absolute value of a positive number is x, when x is greater than 0. The absolute value equals negative x if, or sorry, these should go the other way. You know what I'm saying here. So the absolute value of 20, how far is it from 0? It's 20. The absolute value of negative 5 is 5 from 0. The absolute value of 0 is just straight 0. Be careful here. This negative is on the outside. So the absolute value of negative 3 comes first. We treat it like parentheses. That's a 3. And then this negative sticks. So negative 3. Again, we treat it like parentheses. You do the operation on the inside. So the absolute value of 2 plus 5 is the absolute value of negative 3. The absolute value of negative 3 is 3. All right, some properties to go here for addition of integers. Pretty much all the same stuff. It can be closed. They are commutative. They are associative, just like they've been all along. 0 is the identity for addition. And this uniqueness one is new, but it is part of what we've been doing all along. The idea that A plus its opposite is 0, or its opposite plus A is still 0. So negative 2 plus 2 is 0. And 2 plus a negative 2 is 0. Additionally, thinking about it this way is if I have something plus a number equal to 0, it has to be that that number is the opposite, that missing one is the opposite of whatever's here. If they together combine to make 0, they have to be opposites of each other. Okay? We can extend this property, that should say and, to say that negative times negative A is A, and negative A plus negative B we can rewrite as negative parentheses A plus B. So additive inverse, what that means here, additive inverse is the thing I can add to what I have right here to make 0, okay? I want a sum of 0. So in this first one, the first thing I'm going to do is distribute. So I get a negative 3 minus x. Well, the opposite of this, the thing I can add to it to make 0 is the opposite of each number, is negative 3 plus x. X's would cancel, 3's would cancel, the whole thing makes 0. The additive inverse here, well, the opposite of A is negative A. The opposite of negative 4 is positive 4. That additive inverse would give me a sum of 0. Same thing down here. Additive inverse would be the opposite sign plus the opposite sign. 3 plus x, it would give me a 0. So that's addition. Subtraction works the same way, except subtraction's a little trickier, right? Because we're taking away. So we can use all the same models, and we will. The trick is to remember that when we add 0 to something, it doesn't change its value, okay? So here, I want to do 3 minus a negative 2. So we start here in this first picture with 3, okay? I have 3 positive chips, 3 black chips. What I can do, I don't have any negative chips to take away, so that's annoying. I have to add some into the pile, but what I can do is add sums of 0. So I can add in 2 positive chips and 2 negative chips. This didn't change the value in my circle at all because these are worth 0. Now I can take away the negative 2. Once they're removed, I'm left with 5 positive chips. Okay? So let's try a couple. So if I want to do negative 3 minus 9, okay, I'm going to start with 3 red chips. And I need to take away 9 of them, but I don't have 9 of them. So I'm going to add as many zeros as I need to get 9 red chips. That's 9. So how many did I add? 1, 2, 3, 4, 5, 6. So now I added 6 zeros. You can see them here, so that I can get rid of these negative 9 chips. Okay? Oh, no, wait. 3 take away, oh, negative 3, then take away 9. So I need 9 more. Where did my chip model go? Oh, so these are tricky. This is my brain just fell out backwards a minute. We're going to do this one a little differently. We forgot to, sorry, liberal. We forgot to rewrite this and think about it as addition, okay? So really, I can think about this as -3 minus a +9. We want a subtraction problem here, right? So I want to know what kind of 9 this is. I can think about it as plus a -9 or minus a +9. Since this is a subtraction problem, I want to think about it as minus a +9. That's going to work better. So I have my -3. My apologies for the confusion. I should actually look at my notes. Now I need to take away, that's what this negative sign, this minus says, +9. So I need 9 black chips. But I can't just add 9. I need to add 9 zeros. So I have 9 zeros now. I can take away my +9 chips. What's left is -12. Whew. All right. This one is -4, take away -2, which is actually not so bad, right? I have -4 chips to start. And I'm going to take away -2. Well, I have them there. -4, take away -2, just -2 left over. All right. This last one is 3, take away a -1. So I have 3 chips to start, 3 positive black chips. And I want to take away a -1. Well, I don't have any of those. So I need 1 to be able to take it away, but I can't just add it in. I need a 0. So in order to take away that -1, I needed to add 1 0, which makes a total of 4 black chips. Okay? Charge field model works the same way as what we just did here with the chips. It's just that I'm writing pluses and minuses instead of positives or black and red chips, okay? So for this one, it's -3 minus a -5. If I have -3 to start with, and I want to take away a -5, I need 2 more negative chips. So I can add in 2 zeros. Then I can take out that -5, and I'm left with +2. Okay? -3, take away -5. Number lines are even a little tricky, okay? We do move forward for positive numbers to the right and move backwards for negative numbers on to the left. In subtraction, what you do is when you subtract, you turn around. Okay, this is why in middle schools you see people with number lines written on their floors, because this is how they physically have kids walk on it and turn around. Okay, so here's how this would work. Let's draw a number line. Here we go. It's my 0. Put some lines in. Yours will be prettier than mine, right? Okay, so I'm going to start the first one at 4, right? So this one will be black. So I'm going from 0 to 4 in the positive direction. I want to take away a -7. So normally when I move to the left, when I move -7, I move to the left, right? But when I'm taking away, when I'm subtracting, I turn around and walk in the opposite direction. Sounds crazy, right? So this means go the opposite direction of -7. Well, the opposite direction of -7 is +7, right? So I'm going to go 7 more this direction. +4 minus -7 is 11. Let's try another. -6, we'll think about this as -6 minus a +4. So we'd start by going to -6. 1, 2, 3, 4, 5, 6. There's my -6. Minus a +4. Normally for positive, I move to the right, but this says do the opposite of. So instead of moving to the right, I'm going to move to the left. -6 minus 4, 2, 3, 4, gets me to -10. Okay? And then the last one I'm going to do in green, -7 minus a -6. All right, so we're going to go to -7. 1, 2, 3, 4, 5, 6, 7. Here we are at -7. This is do the opposite of -6. Well, if I do the opposite of -6, I'm going to go +6. So 1, 2, 3, 4, 5, 6. That gets me to -1. -7 minus a -6 is -1. Okay. So then the last model we talked about was this pattern one. Works the same. Kids can back their way into a pattern here, just like we did in addition. Not a big, huge thing. Okay. There are some properties here that are specific to subtraction. One thing to keep in mind is that we can think about integer subtraction as adding the opposite. Okay. This is what we've been doing all along. So the idea that I can rewrite a minus b is a plus a negative b, or a minus a positive b, whatever. So I can rewrite 6 minus 8 as 6 plus a -8. Okay? I can rewrite 2 minus 8 as 2 plus a -8. 2 minus -8, can I rewrite like that? Well, think about it. I can rewrite as adding the opposite. So if I'm adding the opposite of this, I'm really doing 2 plus 8. Minus minus makes a plus. This is how you get there with kids, right there. -12 minus a -5. I'm adding the opposite, so I'm going to add 5. -12 minus 5 is going to be -12 plus a -5. Okay. All right. Almost there. We can rewrite these examples here without parentheses. So really all we do is distribute this negative here. So this becomes a -b plus c. What does this guy become? Well, a, distribute the negative, minus b minus c. You're changing everybody's sign. Finally, now that we're here, remember that subtraction is not commutative or associative. You cannot reorganize subtraction the way we can addition or multiplication. Remember order of operations, parentheses, exponents, multiplication or division from left to right, addition or subtraction. I've told you that I'm not a fan of PEMDAS, simply because it misleads kids. Take a minute, solve these, see what you get. Okay. So for the first one, I'm working from left to right. 2 minus a 5 gets me -3. -3 minus 5 gets me -8. This one, again, left to right, there's no parentheses or there's no other stuff to do. 3 minus 7 is -4. -4 plus 3 is -1. This time, I need to distribute the negative first. I need to get rid of the parentheses. That's the P. 3 minus 7 minus 3. Now I need to follow order. 3 minus 7 is -4. -4 minus 3 gets me -7. Okay? So you can, you'll be following this with the notes from 5.2, but from here, go take a look at the practice, and we'll see how it goes. Thanks.